Okay, guys, can you hear me again? Okay, so this was a lot of the material in section in chapter 5 of the thin textbook. You're going to apply this theory now to look at the American put. Are there any questions before we get started on that? You guys have been a little quiet today. Yeah, we're good. Okay, then we're gonna talk about so American options. Let's see. So American options. So we have like the finite horizon, the finite horizon ones. So we're maximizing over stopping times of the expectation under the risk neutral measure of we're only going to get something. So the finite horizon, right? So there's a horizon here of n. So you're going to get something if the stopping time is less than n. And what we're going to get is this is g tau divided by 1 plus r to the power tau. Right, so we have this gn. This is our intrinsic value process. Right, so we're taking the supremum here over tau. Tau is the stopping time. And tau takes values. If it's a finite horizon, it takes values in 0, 1, 2, up to n, and potentially also plus infinity. So that's the finite horizon version. And then we also have an infinite horizon version. These are called perpetual. Perpetual. Let me just show you. Let me show you the distinction so you can see where we are. So we're looking at the first book. And what we are looking at for the perpetual ones, this is in this section 5 that we've been working in. So the perpetual American put is this example here in section 5.4 that we are about to do. We're not going to be doing 5.3, we'll do 5.2 and 5.4. So this is the perpetual. So here we're looking at a supremum over, and now tau is less than infinity. G tau, 1 plus r to the tau. And now tau is a stopping time, and it takes values all the way up, and it can also take the value plus infinity. So this here is this one here is the one in section 5.4, and this one here is these are the ones over in section 4. And the benefit here is that there is a closed form solution. And here there's just an iterative procedure. There's no closed form solution for the first one. So what I'm proposing is that we look a little bit at this infinite horizon case, because this is where there is a closed form solution, and it really uses what we just done. Right, so the perpetual American put. So you look at a picture. Maybe you can draw the picture with the. Right, so the put is the intrinsic value process is Gn. So this is going to be K minus Sn, the positive part. Whereas if you look at the payoff, so if I look at the European one, the European payoff, this would be K minus Sn, positive part, where n is the expiration date. So if I draw this in my diagram over here, this is my K, this is my K, and out on the x-axis, I'll have the stock price. So if I have a European one, this here is the payoff that I'm going to get. If I have a European one, so let me make the European one in red. If you look at how the stock price, different levels of the stock price would give me different values of the derivative, right? So up on the x-axis, we'll have the derivative price. So for a put, if I'm way out, so the stock price is very, very high, right? Then the value of the put is not very high, right? Because if the stock price is huge, then K minus something huge is going to be negative. So when I move out here, I'm going to get a small European derivative price. So the European ones are the ones in red. And if I look at this here will be something like this. This one here would be the European put price. So I also want to make a picture of the American one. Now the American one is going to be more expensive, as we talked about, because the American one, you have this additional feature that you can call it quits anytime you want and collect. Right? You can call it quits anytime you want, and you can collect the payoff G. And so what that means is that you can always exercise and get K minus the underlying. Right? So that means that the American has to be above this hockey stick. And so what if you are to look at a picture, The American one is going to look like this. This one is the American. And this critical value that we have in here, this value here, exactly when the price of the American is going to hit this hockey stick, this is the exercise. This is the exercise price. This is the critical. This is the critical exercise price. Critical exercise stop price. In other words, when the stock falls below this level, when it moves down here, you exercise. And when you're above, you don't exercise. Okay. So this is a picture that that's good to have in mind when we start doing the analysis. And let me put in some specific numbers in this example here. So, so the specific numbers, it's going to be very specific this time. So the specific numbers are, I have my coin flips. I have my coin flips, psi n, you go to +1 and -1. I'll have my symmetric random walk. Now I am under the risk neutral measure, so I'm going to write a symmetric random walk under the risk neutral probability. So half and half, +1, -1. Mn is just going to be Mn -1 plus the coin flip, and it starts out at 0. And then I'm going to get the stock price. The stock price is now defined as S0 times 2 to the Mn. I want S0 to be 2 to the J for some J. So you see this is a model we've seen before, right? If the first coin flip, is heads, then S1 is equal to the initial value times 2. If the first coin flip is tails, then the first stock price is equal to S0 divided by 2. So this is the model that we've had many times before. So up and down is equal to 2.5, and the interest rate we're going to be working with is 25%. The stock price that we're going to, the strike price we're going to be working with is 4. Right, so the example is, we start out here at 4, and then we go up by a factor of 2, so it goes up to 8, it goes down to 2, and then it keeps going like this. 1, 4, 4, 16. And so on. Right, it's an infinite long, infinite limited coin, infinite many coin tosses. And so what I'm interested in is the American put price at time 0. So I'm going to call this a VS0. So it's the maximum over stopping time. So now it's perpetual. Perpetual American put price. So stopping times top omega is something in 0, 1, 2, union infinity. And then the payoff is discounted 1 plus r to the power tau, and then you have k minus s tau, a positive r. Right, so what's this value? Are we all good so far? Are there any questions up to this point? This is an optimal stopping problem. I'm trying to maximize these expectations that I have over here. So maybe just a few things to note. One could think about what happens if I'm plus infinity here. If tau of omega is equal to plus infinity, if tau of omega is equal to plus infinity, then what we're looking at up here is that there's no indicator here, and so we have potentially a problem because what about this s at tau at that point? What is that equal to? Because we don't have s infinity of omega defined. But the key is, so it's very similar to that calculation we had earlier. So the thing to observe is, if I look at k minus there was a question in the chat. Let's see. Isn't tau equal to 1 since it goes above 4 in the first step? How do you know that? How do you know that it goes above 4 in the first step? It could also go to 2, right? So I don't think we want to exercise at time 0, right? We're going to get 0. But what about here? Do we want to exercise if it gets down here? Well, I don't know. What do we want to exercise if we get up here? Or it goes up to 8. I don't want to exercise. Actually, I'm not sure I can follow you. At time 1, the stock price can be either 2 or 8. And I don't think you want to exercise if you're in the upstate. And, you may or may not want to exercise in the downstate. If you exercise in the downstate, you're going to get payoff of 2, and this might be good enough for you. But for sure, in the upstate, you're not going to exercise. You're only going to get 0. But that's why the picture is the way that it is. But you start out somewhere with the stock price, and you want the stock price to drop sufficiently before you're going to exercise. So here the stock price just starts out at 4, but you want to have it for you to exercise. You're going to drop down. Yeah. So the call, we're not doing the call. We're looking at the put. Okay. So we're trying to figure out, like, did I just forget to write? Did I forget to write the indicator here, or what happened? Well, let's just have a look. So if this stopping time is plus infinity, which is theoretically possible, and we are allowing for that. And what about this? What is the stock price at infinity? Well, this is not defined. But we observe now here that Sn, positive part, right? This is as before, is bounded by k, and is bounded from below by 0. We observe this, and what about 1 plus r to the power tau? Well, if tau is equal to plus infinity, this one here is equal to 0. Right, so you combine, and if I take 0 times something bounded, you're going to get that k minus s Sn times this indicator of 1 plus times 1 divided by 1 plus r to the tau. This is bounded. This part, the first part, this is bounded. The second part, this is equal to 0. So this is going to be equal to 0 for all values of Sn. So in other words, so choosing tau to be plus infinity, it gives a 0 payoff. So this is not optimal. In other words, it's not going to be optimal to have a random variable. It's not going to be optimal to have a random variable that takes the value plus infinity. So we can scratch that out. And this is quite different from the call. So compared to the call. Now, of course, he asked for the call, so compared to the call case. And so then you will still have that 0 is bigger than this Sn minus k positive part. But the upper bound, there's no upper bound here, right? The upper bound is, well, it'll be Sn. So then, if I have 1 plus r to the power tau, this is equal to 0. If you try to combine, then you would have something like S tau times 1 over 1 plus r to the tau. So it's true that this thing here is 0, but what about this one? Well, this one could be plus infinity, right? So then the product, you don't know what that is. So this argument we gave up here uses this upper bound. You will not have that upper bound for the call case. Simply because 0 times infinity, this can be anything in the limit, right? So for example, if you take x times 1 over x, right, and I compute the limit, this is going to be a 1. But on the right-hand side, this is also equal to plus infinity times 0. Right, so you cannot say that this is equal to 0. Indeed, here it's equal to 1. Right, so this is not true. In the put case, we don't have to worry about stopping time taking on the value plus infinity because it's never going to be optimal. It's never going to be optimal to choose such a stopping time. Any guesses on what the optimal stopping time here is going to be? This is my tree structure and it keeps going. What kind of an optimal stopping time are we looking at? Well, we want the stock price to, we don't want to exercise immediately, right? Because k is equal to 4, you exercise immediately, we get nothing, right? So there should be, you're going to wait for the stock price to drop. So how long are you going to wait? Well, I don't know. So let's try a passage time. Let's put in a passage time. So this is our conjecture. The optimal exercise time is when Sn drops below a constant. Right, so this stopping time over here that attains the supremum, right, this is going to be equal to E tilde 1 over 1 plus tau hat k minus S tau hat positive part. So the optimal exercise time, this is this tau hat, the one that attains the supremum. That optimal time is going to be when the stock price drops below a certain level. So this is the first passage time. But what level? What do you guys think? So this is our example. K was equal to 4. So what should we put in here? What should be this exercise? This critical value, what could it be? Well, it's going to be less than 4, right? So 1, 2, 3. How do we figure out which one is the optimal one? And so on. Before I launch into the next set of calculations, I just want to make sure that what we're doing at this point, we're building up intuition for what we should be able to see in the math that is to come. So the first thing we did was we had a little picture that kind of gave an idea about the relationship between American and European ones. Right? So American ones are more expensive, right? So the derivative price of the American one, that's the darkest line. This is above the red line, which illustrates the European put price. And there's a connection with the American one because we have this ability to always exercise. Right? So this here, that triangular structure, that hockey stick, that's the intrinsic value process. It's also sometimes called the obstacle. And it's an obstacle because the put price has to be at or above it. You can always exercise and get the intrinsic value, so the price has to be above it. Like if you can always get $5 out, if you have that right, I mean, that right is at least worth $5. So it has to be above it. It's not true for the European one. Indeed, here it's below. And so now we are thinking about like, okay, so where is this critical point? And that's what, so we're conjecturing that there is such a critical point, and furthermore, that critical point doesn't vary with time. It's the fact that we're looking at an infinite time horizon that makes this point not vary with time. If we were looking at a finite horizon, the first case here, we would not have a constant level. This level would depend upon how much time there's left. Just as when we were rolling that die last time, your decision to call it quits or not call it quits, that depended upon how many rolls you had left. Right? If you have infinitely many rolls left, the stopping time is going to be the first time that you roll a 6 in that game, right? Because you're ultimately going to roll a 6. And of course, there you do not have the boundary that's critical. Does not depend upon how many rolls you have left. So it's the infinite time horizon that allows this critical stock price level to be independent of time. And how do we figure out what it is? And so this is what we want to do now. Watch that. Well, so what is it going to be? So we have, so V is the price. So like V is 0. This is the This is the American put price. And we have a recursive way of doing that. We know, so if you look at the European one, we would iterate. Right, so we would look at, we would iterate. So we would have like your Vn of Sn would be, this would be the conditional expectation of 1 over 1 plus r of Vn plus 1 of Sn plus 1 given Fn. So you would have, this would be, in this setting here, it would be a half because those are the probabilities, the reverse neutral, 1 over 1.25, right? And then you would have your Vn plus 1, and then you would have your Sn times the up. Up was 2, and then plus Vn plus 1, and then it would be Sn times a half because that was the down factor. Right, that would be the European one. And then you have the finite horizon American. Then it will be very similar. This would just be the max. Because you can exercise early. So you're going to be looking at what would be my my pay of GM. This would be K minus Sn, positive part. And then the price you had up here, 1/2, 1 over 1.25, and then Vn plus 1 times 2 Sn plus Vn plus 1 times Sn divided by 2. That would be the finite horizon American. And so now we have the infinite. So for the infinite horizon, there is a this is independence of time because it doesn't matter how many rounds we've seen. There are still infinitely many rounds left. It reminds me of a story. So let me tell you a story, maybe, just to change things up a little bit. Has anybody heard of something called Hilbert's Hotel? So this is the hotel that is never full. And it has to do with this play on infinity. And so Hilbert's Hotel is never full. And so how did that work? There are infinitely many rooms in Hilbert's Hotel. And so and all the rooms are full. And so what happens is that a new customer shows up at the reception and he needs a room. And even though all the rooms are full, and even though the guy that shows up, he doesn't have a reservation. So what did he do? He asked everybody in the hotel to go down one step on the hallway. So we go down one room on the hallway. Right. So everybody goes out of the door. You shift one to the right, and then that's their new room. Right, so you walk. Everybody walks down one. Okay, so everybody now has a room again, and the first room is now available. Right, so the customer that showed up, he gets the first room. Everybody else moves down one room. Everybody's happy to have a room. And that's Hilbert's Hotel. And it's a play on infinity. What it shows is that infinity and infinity plus 1, those are the same quantities. And this is what's going on in this problem too. Even though you have seen a number of coin flips, you're still missing to see infinitely many. You still have infinitely many coin flips to come. And this is something that is setting the perpetual American put strictly aside from the finite time horizon American book, right? Because for the finite time horizon, there are only 8 coin flips, say. There are only n coin flips that you get to see. So it matters whether you've seen 5 or you've seen 4. Think back to the game that we played with rolling the die. If you only have 3 chances, it matters what comes out in the first, it matters what comes out in the second. But if you have infinitely many, it doesn't matter. Time becomes irrelevant because even though you've been going on for a while, there's still infinitely long left to go. So this is very similar to the Hilbert Hotel story that I just told, and it seems like some of you have heard that one before. So what happens in the infinite horizon case is that this n up here disappears, and you end up with v of, let me just call it v of s. V of s is going to be given as a max. Then this is k minus s, positive part, 1/2, 1 over 1.25, v of 2s plus v of s divided by 2. You can call it Sn here, but yeah, we could have written this one here as v of n of x. This is equal to max k minus x 1/2 1 over 1.25 v of n plus 1 2x plus vn plus 1 x over 2. It's just a dummy. And the same thing up here, of course, you can put in an x instead of Sn. Here I'm calling it S for the stuff. So this is my equation, and we want to solve this. So here's what we have. So try to solve this thing. This equation has many solutions. And of course, it's not something we like, right? Here, you tell me what Vn plus 1 is, and you're going to iterate backwards and get what Vn is. So here we're looking at this part. And this one has many solutions. And let me list a couple of them. First one, so let me list, the first one could be V of S being 4, so keep in mind K here is 4 minus S. This is when S is small. And it could be 4 divided by S when S is big. So that's one guy. Another solution could be V of S is 4 over S. So take these two, plug them into this, and you'll see that it holds. And then we can look at a picture. So we're going to try to recreate. The picture we have down here. I'm going to take the red stuff away and just focus on the American part. So on a picture, what do I have? I have it's a straight line down to 2. So I have my obstacle. The hockey stick goes from 4 to 4. And now here 2. The first one, it follows the hockey stick and then it slides out. So this was the first one. And if I look at the second one, is this V, so it's 4 divided by S. So it when S gets to be small, right, when S gets to be small, I'm dividing by something very small, it blows up to infinity. I have this guy. right? And then do the same for OS, do the same when S is bigger than 2. So these are my two solutions to this equation up here. So which one is the right one, if any? So how to find the solution? How to find, guess the correct solution. We'll verify in a bit, then verify later. How do we come up with a good guess here? Well, what happens when S is big, right? S is our stock price. What happens when you're far out here to the right? Well, if you're far out to the right, then this term here should dominate. When you're far out to the right, you're not exercising. So for S big, we will have the V of S is the second term, right? V of S is going to be the second term. So this is 1 over 2.5, and then V S times 2 plus V of S divided by 2. So we need to be able to solve that. So maybe we can try V of S to be a power function. Okay, so then I'll have the left-hand side of SP, the right-hand side will be 2.5 times SP 2P plus the other one will be SP divided by 2P. So this is the same, divide over with SP, we're going to get 1 is equal to 2 divided by 5 times 2P plus 1 over 2P. And this is the same thing as saying that P is equal to either plus minus 1. All right, so this is our guess. So when P is equal to 1, I get S. When P is equal to minus 1, I get 1 over S. Okay, so we take a linear combination. So linear combination V of S is equal to AS plus B divided by S. So that's my guess. But what about for two constants? A and B. We need to find them. So let's try to find them. So let's go back to the picture again. If I'm looking at the black curve, when the stock price goes to plus infinity, the American put price goes to how much am I willing to pay for an American put if the stock price tends off to plus infinity. Well, if I look at the limit as S goes to plus infinity of V of S, I want this to be 0. But that's the same thing if I have that form to say that A is 0. So for large S, V of S is equal to B over S. for small values, for small s, well, for small s, can you not hear me? So let me go over it again. Can you hear me now? Don, can you hear me now? Can anybody hear me at this point? Yeah. Some people can hear me. Dawn, I'm not sure. Can you hear me, Dawn? Let's just give Dawn a second. Okay, so what's going on here is we're doing guesswork. Right, so this can be quite frustrating. It's been quite frustrating to see a math course being taught with guesswork. It is, however, not uncommon. For example, if you are to solve an equation, it's okay for you to guess what the solution is. But this verification has to happen subsequently. Right? So if we can verify subsequently, we're good. What we're doing is we're coming up with a guess about what this black line is. We're guessing what it looks like out here for large values of s, and we're guessing what it is looking like for small values. Right? For small values, it's going to be a straight line. For big values, we don't know what the shape is, but we came as far as to say that it's going to look like something like 1 over s. 1 over s for large values times a constant, but for small values, it's just going to be this straight line. Right? So for small s, v of s is going to be this k minus s positive part. Excuse me. Right? And for small values, s is definitely going to be less than the 4, so this will be 4 minus s. So I know what it looks like for big values, I know what it looks like for small values. Then we equate. There's going to be some critical value where it goes from being what it is here to being what it is up here. Is to find a critical s hat and maybe a b, such that what? Well, such that when I do 4 minus s hat, I'm going to get exactly b divided by s hat. But now I have one equation and two unknowns. Now I have two equations and unknowns. Right? So I'm equating what happens when I come in from the right. When I'm coming in to the left, this critical stock price is what I called S hat. What I called S hat. What else can we do? We have two equations and two unknowns. Well, maybe more is true. So this here is what will ensure continuity. Maybe more will be true. Maybe we'll also have differentiability. Differentiability. If I can spell it. That's not spelled right. Differentiability. So we compute the derivative of the left-hand side with respect to s. This is going to be minus 1. And we compute the derivative with respect to s of the right-hand side. This is going to be minus 1 over s hat squared times a b. So now we have two equations and two unknowns. We solve. we're going to get B is equal to 4, and we're going to get that S hat is equal to 2. Right, so now we have our conjecture. So all in all, we're conjecturing that our V of S0, this is equal to 4 minus S0. This is when S0 is less than 2, is equal to 4 divided by S0. This is when S0 is bigger than 2. And tau hat, this is the first time when Sn gets to be less than the critical level, which is 2. Right, so this is what we claim. We claim that, all in all, we claim that this here satisfies that when I compute the supremum over tau of E of 1 divided by 1 plus R to the power tau, K minus S tau, positive part. When I maximize over stopping times, this here is going to give me 1 plus R and then the tau hat times K minus S tau hat, positive part, and this is exactly equal to V of S0. So this is our guess, and this here is this needs to be verified. Any questions or comments up to this point? So there are lots of loose ends here, right? We made a bunch of guesses and conjectures and hand-wavy arguments, and like for example here we demanded continuity and we demanded differentiability. Like the last part, this differentiability, this is called smooth fit. It's called smooth fit. It's also sometimes called the high contact principle. In this particular example, this holds. There is really differentiability of the value function. But it's not always true that the value function is differentiable. Here we have continuity. Continuity, this is something that holds sooner than differentiability. What is really perplexing is over here on this page. We had two solutions, right? We had two. We're looking at the equation, right? And then that equation has two solutions. It has many more. You take combinations of these. It's going to work out fine too. But what's wrong with the second one? Like, you can somehow see that the first one is smaller than the second one, right? So this is maybe something to note here. Something to note here that the second one, 2 is bigger than 1, right? Because the red line dominates the black line, right? Do the same out here, but then inside here is bigger, right? For small x, for small s, 4 over s is strictly bigger than 4 minus s. So where is this? So why is 1 correct? There's somehow a smallness property. Where does this smallness property come from? So this is just one question. Where does the smallness of V come from? I mean, ultimately, the place that it comes from is the definition of the supremum. So recall what the supremum is. Right? If I take the supremum over xn, this is a big number. It's a big number, right? What does that mean? It means that it's bigger. It is bigger than xn for all n. And it's the smallest such big number, right? In other words, if y is also a big number, well, then y is also going to be bigger than the supremum of xn. So it's this smallness property. This is ultimately coming from the definition of this supremum. Okay, so how do I justify that? How do I justify that? Okay, so now we're going to be moving into verification. Right, so we're moving in to saying, okay, so this is what we have. We define the stopping time to be the first passage time when the stop price drops below 2. Okay, we define this function here, and now we're claiming that this supremum here, this is exactly that value function. So we'll take the supremum over tors, compute this expectation of each one of them, take the biggest, and we're going to get this thing, and we're going to get the same thing as when I plug in here that particular stopping time I have up here. Okay, so we're trying to figure out where does the smallness come from? Well, it comes because there's a supremum here, and this supremum is defined in terms of a smallness condition. So ultimately, it comes from the definition of a supremum, but I mean, this is a far cry, right? There's no mentioning over here on this side of this page of anything that has to do with tau and so on. So there's no way around it. We have to dig in. Verification. And there are a number of steps to it. The first step in here is to say, go back to the definition of the perpetual analytic input. So if I look at the definition here, this is my V0. This is my V of S0 by definition. How do I do this? Well, I would, one thing we could do is if we take tau to be 0, right? I'm taking the maximum overall stopping times. In particular, I could pick tau just to be exercise immediately. So if I do that, then I would get that V of S0. This is the maximum, so this is going to be bigger than well, E tilde G0, and G0 was equal to K minus S0 positive part. So it's true that the value function, it must dominate this difference here. And then the second step, we're claiming that what are we claiming? We're claiming that so what is the claim? We're claiming that V of Sn, so this would be E tilde 1 over 1 plus R, and then a supremum over tau, and then here will be tau minus N. I'm conditioning on N. And then it'll be K minus S tau, positive part. We're claiming something like, we're claiming that this object here is a supramartingale. We're claiming that Vsn divided by 1 plus R to the nth, this is a supramartingale. Right, so this is the claim. And how would one go about proving that? We're running quickly out of time. The third one that one would go about doing it is that, given that we can do this, the third part we would do is that 1 over 1 plus R of V of Sn. This is the smallest. This is the smallest process satisfying 1 and 2. This is the smallest process satisfying that V of Sn over 1 plus R is a supramartingale, and V of Sn dominates K minus Sn positive part. And then the last point being, so this is the supramartingale part, this is the smallest part, and then the last part is to show that if I take V of Sn, but here I've stopped it at this tau hat divided by 1 plus R n minus tau n hat. This is a martingale. Right, so these are the steps that we have to carry out to do verification. We only did a little bit of the first one. We didn't do 2, 3, and 4. I'm not sure I can. We only have 5 minutes left. There is just no way for me to plow through all these steps in 5 minutes. Maybe I can show you where you guys can find these arguments. So we're working over here on page 129. So here you'll see that there are these arguments that we had listed, and you dominate the obstacle. You have a super martingale property, and then you have the smallness property. And so here are the proofs, he outlines them, and then in the end, the crucial property comes. Where is the crucial property? Where is the martingale property? That's somewhere else. Yeah, so the martingale property, this is written over here when he wants to show that this is the optimal time is exactly when the value is equal to the obstacle. So in that picture here, this is exactly this crucial point when the obstacle, which is the straight line, and the price is the black line. When these two guys meet, this is when it's optimal to exercise. So in our case, this is the first time that the stock price gets to be 2. Then the crucial step in this proof is to check that you have a martingale property here. This is the martingale property. Okay, so these were the 4 steps that one would need to justify if one were to go ahead and justify why our guess is exactly correct. We'll be out of time, so if you're interested, you can find the arguments in the textbook. I think this is, I'm running out of gas, and I can only imagine for those of you that are, it's pretty late some places in the world, and I think this is a good time to call it quits, unless there are some questions here at the end. Are there any questions or comments before we? Okay, if that's not the case, then please use. So tomorrow morning there'll be a practice session with Xiao, and then on Thursday and Fridays there will be office hours, and then we'll continue with American options on Tuesday next week. Alrighty, have a good day, have a good night, and if you have not voted yet, please go out and vote. Last call, and then I hope to see you guys next week.